Imagine a high elevation plateau at first light. The horizon is washed and muted. Rows, as a migratory herd of caribou for our purposes here, though any wide ranging species will suffice, moves in a coherent yet always slightly improvisational pattern across an expansive landscape. Now, scale up the observational enterprise. Not one scientific field is monitoring this movement, but instead 40 teams are doing so, each drawing on their partial archive of ecological knowledge to predict migratory patterns. Teams begin with last season's meticulously annotated field logs, and others will carry drone imagery, and others will look at ethnographic notes from local guides who have watched the animals for generations move across this geography. Each research group holds a slightly distinct hypothesis about the herd's present location and their emergent trajectory. Decisively, none of these perspectives is basically incorrect. They all respectively show an adaptive interpretation formed under the conditions of informational insufficiency and environmental circumstances that are not yet accounted for in the models that they're using. Regular intervals of this transmission from one of the tagged animals may survive, and the single data point acts as a corrective constraint. Each field needs to adjust its infrared trajectory if a projection diverged substantially. If presumed water sources have dried out, the map is going to shift. The projection or the forecast is going to shift. So if that forecast or prediction is broadly content with that new signal, the adjustment is modest. Through the iterative cycles, teams continuously refine their reconstructions. They continually update them, not expecting to be right every time, but to get closer and closer to a prediction that can be considered valid and reliable. Over time, their estimates begin to exhibit recognizable structures and patterns, and in some conditions, the various inferred paths converge tightly. And in others, the distribution is diffuse. It's unmistakable as a signature that the animal's behavior in this case is sensitive to small perturbations, or the observational network they're using is insufficiently constraining them from making better predictions. So substitute the herd for the atmosphere in this case. The atmosphere is pinging with satellite retrievals and Doppler radars. And field teams with dozens of parallel models realize that what constitutes an observational ensemble can come together in what we know as a weather forecast. A disciplined and continuously corrected estimation exercised in the presence of uncertainty is the aim of atmospheric science and science in general. And the continuous correction estimation is the goal of science in general. Effective public communication about science requires sharing the full suite of information, and that includes the information about uncertainty. The most probable trajectory is not a fixed, absolute claim. The most plausible alternatives, the confidence intervals, the schedule for subsequent updates, all of these play a role in how we understand what a forecast prediction is implying. We know that weather predictions can be inaccurate. National, international agencies ingest streams of information from radiosones and weather radars and aircraft, ships and buoys, surface stations that are all coordinated under the World Meteorological Organization's global observing system. These observations don't fill every cubic kilometer evenly. They're patchy, noisy, and that matters when we want to quantify something like uncertainty, and also when we want to try to explain it. The World Meteorological Organization's data assimilation program exists to optimize how disparate data feed into models. Let's consider the case in January of 2019 amid an anticipated snow event in the nation of Jordan. Those disparate data feed the models, and the Arabia Weather Service, which is considered highly reliable in the Middle East, and especially in Jordan, issued a confident, assertive, high impact forecast that implicitly elevated one potential scenario to the status of inevitability. It's going to snow tomorrow. There's no question about it. Obscuring, though, the broader ensemble of plausible outcomes is inferred in that claim. Immediately following this announcement, businesses decided to close down schools when the predicted snowfall businesses decided to close down, schools began to close, people began to stock up on bread at their favorite bakery. When the predicted snowfall failed to manifest, though, the public experienced not simply an inconvenience, although that is primarily their experience with this particular misfire. There was also a breach, though, that had been established of credibility. This organization was known for being credible, an erosion that reflects deep pretensions between the probabilistic systems and categorical messages that those systems put out as a result of their predictive models. In this episode today, we're going to examine how this rupture can unfold, how probabilistic signals become reified as certainties, and then how image repair strategies in certain contexts can be studied as another decision-making moment that demands more than just retrospective justification, and how institutions should cultivate modes of uncertainty communication grounded in humility, transparency, and procedural rigor. That's tonight on Decisions at the Fulcrum. This storm was not supposed to be an ordinary blizzard. It was supposed to be something cinematic, but what we got instead was an anticipatory energy from people in the cities that seem to acquire this when something might shut everything down. In Amman, Jordan, the WhatsApp group started to buzz. The bakeries were seeing noticeable upticks in bread sales. Families are starting to joke about a visitor who's coming wearing white to see them and quietly rearranging their week just in case. And across the television networks in Amman, a similar headline is recurring. The headline was snow expected above 900 meters in Amman. If we were to look at this as if we were to think about it as a template of what a breaking news headline might say, we could say that there is a classic sensational headline skeleton that exists in the media and messaging world when organizations want a rhetorical punch. You have an actor, so you might have the news agency, or you might have the meteorological organization or Weather Arabia. You have an actor or an institution having a high impact on some critical development or decision amid an immediate context or the immediate stakes at play. The idea of certainty is baked into this, while acknowledging uncertainty, though, can be really important within the same statement. It's good to sometimes take a break from reading headlines for this reason. But let's think about Amman in 2019. The message was remarkably consistent. The kingdom is going to be affected by a cold, moist air associated with a classified low pressure system. Snowfall is expected on Tuesday evening into Wednesday. High elevations starting at 900 meters is just an example above the sea level. Media outlets mostly replay that official department message without a lot of sensational additional language. The Jordanian media credibility monitor, known as Akid, which later audited the coverage, did find that the newsrooms largely stuck to the straightforward source statements about the snow above 900 meters. But the headline structure does a subtle thing. It implies a direct boundary below 900 meters and above 900 meters that have to do with rain above 900, snow. If your neighborhood sits at 930, you might hear, yeah, we're in. If you're at 880, you might think, oh, maybe we're just below this fixed line. To assume that this is a fixed line is the aspect of certainty that comes through in the way that we present forecasts and the way that we present headlines. And then the night in question happens. It started to behave roughly as advertised. There was a lot of cold, there were winds, there was a wintry precipitation, but in much of Amman, especially the neighborhoods where people imagined that they were safe above 900, they imagined safely above 900, the residents began to wake to a rain-damp street and bare pavements with no snowpack. No road closures, certainly no white-dressed visitor coming to see them. The immediate sense was that people had to rearrange their lives for something that would never arrive. That's frustrating. It is likely preferable, in my view, to having to perceive that surprise white visitor when I wake up and see the street covered in snowpack and ice, and I'm wondering, how am I going to get out of the car? And I'm just going to have to wait for it to melt. But the immediate result isn't a physical damage in this case. It's something in this case that's more intangible, in a sense that people have rearranged their weeks, their days for a snowstorm that's never going to happen. Social media would do what it does best in this case, circulating a story that may or may not happen, but circulating it as though it's inevitable. Television packages compile sarcastic memes, and you have people being interviewed about filling up with gas to stock up. But where'd the snow go in Amman? The story at this point is no longer about the story. It's actually about, how did we get this wrong? Why are we sitting here in the rain? Both the National Meteorological Department of Arabia Weather responded. They emphasized that the underlying guidance and numerical weather prediction models that had indicated a strong polar air mass, the error stemmed from how those models handled a crucial detail, the fulcrum point when things begin to turn. If we identify that point about the core of what the cold air would penetrate deeply enough and low enough in the atmosphere to support snow below 1,000 meters. In one explanation, Arabia Weather stressed that the models misjudged the depth of the cold layer, and the translation from probabilistic model space to categorical human language is what broke, though, in this case. What broke our planning and our interpretation. At first glance, the Arabia weather system may appear to stumble as a result of the overconfident snow forecast. There's always error, though, that's baked into these models. And people, when they're planning their day, they do want a degree of certainty. It's important to keep in mind that there are certainties that are possible, there are certainties that are maybe claimed but are actually not possible to be a guarantee. But so uncertainty is something that, rather than trying to reduce it to zero, try to manage it. When organizations respond to a misfire with the rhetorical self-protectionism, they widen their credibility gap to the point that there's an enormous gulf between what people perceive them to be doing and what they think people perceive them to be doing. To link this case outward, let's look at Benoit's image repair strategy today, which has been used quite a lot since the 1990s. Benoit argues that when an organization is perceived to be responsible for an offensive act, whether or not they are actually responsible, whether that's factually accurate, the only route to reputational recovery is strategic communication that mitigates the perceptions of responsibility or offensiveness that they seem to have generated. In the case of Arabia Weather, it's illustrated why Benoit's strategies could be chosen selectively based on the context and based on the audience. In the article that this case study of Arabia Weather is presented in Sawal 20 et al. 2020, they showed that the agency used by Arabia Weather in this case illustrates exactly why image repair strategies need to be chosen selectively. They found that the agency here did a trio of strategies like good intentions, bolstering, for example, in the response to getting it wrong. They said, hey, we're usually accurate. That's what bolstering is. Minimization by saying, let's not exaggerate. It's going to be wrong from time to time. Okay, true, but you're still minimizing what the public is going through in that particular moment. So it's better just acknowledge what they're going through rather than like reinforce your own credibility at this time. You can do that later. These combine, the bolstering and minimizing can combine into evasion of responsibility and a reduction of offensiveness strategies. They attempt to explain away rather than accept and acknowledge and concede that they had a role to play in this. Research literature has repeatedly shown that these strategies perform poorly in crisis situations where the public experiences some perceived, in many cases, actual harm. Stronger strategies like mortification and corrective action, I'll talk about those in just a minute, are more effective because even using the strategies that say we had good intentions, we are actually very accurate most of the time, are not as effective as mortification and corrective action. Even if the harm is only wasted work days and public disruption, the idea that you want the public to continue to listen to your forecast predictions is a motivation to get these image repair strategies and this communication right. You want to continue to maintain that credibility in the one thing that you do. In the Sawala's case study review of this Arabia Weather case in 2019, they confirmed that stakeholders expected an apology and a corrective action, not just a justification or reminder that they were usually accurate. Like a microcosm of global crisis communication failures across sectors, whether it's public health, whether it's food safety, weather forecasting, aviation, finance, economics, there are three recurrent failures that emerge in these predictive models. The first one is that there's a premature certainty signaling. So in the case of Arabia Weather, calling a grade 3 snowstorm fails to materialize has echoes of being overconfident. Whatever they are calling, though, this is similar to Boeing 737 MAX statements, and very consequentially, the Boeing 737 consequentially, and the Flint water crisis, where officials were very defensive in their messaging. Statements are more consequential than in the Arabia Weather case in this particular incident. With weather forecasts, stakeholders will include people, in other words, who need to know about the weather. They need to include those people. This will be families who are reorganizing their schedule. This will be schools and universities who are also reorganizing their schedules, transportation systems who are reorganizing their schedules, government agencies who are planning for the next day, and businesses that are deciding whether or not to close early. So the weather forecast being explained in a certain way, it is just a day that they missed. But if we take this logic and this pattern and branch it out into other contexts, you can see how when an organization communicates to everyone as if they are the same audience, they are communicating effectively to no one. And that echoes a lot of the broader scholarship on image repair, requiring segmentation, not just generalization of approaches and strategies. We've seen that image repair strategies are important when organizations, when individuals, when institutions get something wrong. And this happens frequently. It's just a part of the process of discovery, having false starts when you go in and you reset and then you keep moving forward and eventually get to the answer that you're aiming for. When we think about what it looks like to trust institutions, to trust organizations, to trust individuals, we can look at what it is that's driving our perceptions of predictions, what we consider to be the central focus of narratives, like when the weather predictions inaccurate from an institution that I trusted changed my entire day because of those predictions. When they get it wrong, it can be seen as something that it causes me to question the reliability of my weather apps, for example. A few other examples of this can be seen when forecasts can get something wrong because of outlier cases. And there are more and more outlier cases in terms of weather these days. And it goes the other way sometimes when we could talk about storms that manifest in ways that are actually stronger than they anticipated. Let's think about Cyclone Freddy in 2023. It's the longest lived and most energetic cyclones recorded in when we on record. Early forecasts though were struggling with the intensification windows and the tracking and the possibilities of things like rainfall and flood potentials. And the regions like Mozambique and Malawi were hit harder than the initial forecast had called for. Some humanitarian agencies also argued that when it came to the early warnings, they downplayed the persistence and the re-intensification potential of Cyclone Freddy. Public discourse, especially in Malawi, at the time also focused on whether the weather authorities should have known the storm would return for a second landfall cycle. Trust can be lost, but it's not about accuracy of a forecast as much as it's about the shock that comes from the uncertainty and from the change in their expectations. When a forecast is struggling with an outlier storm like Cyclone Freddy, it creates a sense of reputational anxiety that fractures in people. That reputation becomes foremost as a consideration for over the explanation of uncertainty to the public. When we sense reputational anxiety and fractures within a group, even with scientists who do have access to the best approaches that we know of for predicting especially severe weather under chaotic conditions, it can become an expectation in most of my lifetime. There's an expectation there will be extreme storms, and forecasting for a normal storm seems less and less reliable. Communicating uncertainty, though, when we report our models and we report forecasts, rather than just reporting the hazard, is essential. That's what I'm getting at. The expectations that we have for an event that we assume is going to happen, that shapes our perceptions, that frames our day, the reputational cost often occurs when models that are predicting them are rational and reasonable and reliable most of the time. In 2023, when that extraordinary storm like Cyclone Freddy moved across the southern Indian Ocean from northwest Australia to southern about a third of the Earth's circumference, meteorologists were aware that Freddy was unusual from the perspective of an expert meteorologist. It triggered a special scrutiny precisely because it defied the expectations that experts and non-experts had, defied the expectations that were instilled in people that were affected by or interpreting a cyclone's lifespan and the re-intensification of it. So did they anticipate Freddy's unusual behavior? Partially, yes. But even with the attention to the unpredictability, several factors always limit how anticipated the full severity of a storm, the lifespan of a storm, for example, could be for a cyclone or for a blizzard. And when we have factors like environmental variability or storms that have multiple phases, the forecast can become highly indeterminate, even if we recognize a wide range of possibilities that could occur. Conveying that to the public, to the decision makers in a way that balances urgency along with credibility in the face of uncertainty remains an extremely difficult task. Forecasts and the model divergence that happens can show a widespread for the path that Freddy could have taken, as well as the duration and the intensity. Reports that turn into the forecast, even the final forecast, should come with a sticker that says error possible, be careful what decisions you make, and pay attention to updates as they unfold. Don't get one claim that we make fixed in your mind as meaning one thing, because there should be error bars that are presented to the broader public, translating the forecast and the model into a decision that individuals can feel confident about. Whether or not to evacuate, whether or not to continue with that vacation, whether or not to stock up on bread at the bakery, for example. The forecast and the model divergence into a decision that people feel confident about can be the goal. And meteorologists might have anticipated some of the storm's behavior during Freddie, and they recognized the potential for a long-lived storm, but they couldn't reliably anticipate all of the behaviors before they happened, especially not with the precision that impacted the populations. Now, when a storm like that occurs again, they may look at what happened with Freddie and be able to better predict the behavior of that storm. But it's always an ongoing activity. It's an ongoing activity of discovering and rediscovering and testing hypotheses and coming up with really interesting findings. Image repair, or image restoration, as it was originally termed, has become a core framework in crisis communication. It looks at how individuals and organizations respond rhetorically when their reputations are threatened. Image repair offers a taxonomy of message strategies that relevant actors can deploy when they are faced with accusations and suspicions of wrongdoing and certain failures in terms of their role or their task or their observation. Let me go through each of these quickly. Benoit's image repair strategies begin with denial, simply denying, I did not do this. This did not happen. I was not involved in it. I am not to blame. The responsibility is with them, not us, not me. Most defensible when accusations are actually factually incorrect. There's not a perception issue in this case. If it's factually incorrect, the denial can be very effective. It works when responsibility is not on you. The next one is the evasion of responsibility. This is the second one. This is a provocation where we say, well, we were provoked, or well, we lacked crucial information, or well, we meant well. This gets often attributions of blame. It's also perceived as excuse making, especially if it's repeated or contradicted by the organization's approach to the event. When it comes to reducing offensiveness, in this case, you might have, let's say that there's a storage unit. This is an unfortunate event, and we will compensate those who are affected. That's an example of reducing offensiveness. Bolstering, minimization, and differentiation, sometimes compensation. The next one is corrective action. Corrective action has to do with a plan of correction, promising to fix what happened, make it better. We're fixing the problem, we're investing in new safeguards. This is consistently reported as a strategy that works. It's perceived with more sincerity. Specificity of reforms are crucial in this case. The important part, the implementation of reforms, is the most important part in order for this to be effective. And lastly, mortification is an expression of remorse. We will accept full responsibility. So it's effective, it's clear, and audiences can be very forgiving. Audiences seek some contrition, though. It can be very effective if you say we accept full responsibility for getting this weather prediction wrong. Effective image repair involves the clusters of these strategies, though. We can add together mortification with corrective action, with bolstering a broader concept that has to do with maintaining face or social image, and a set of perceptions that are held by the relevant audiences about a person or an organization. The image that the organizations are trying to repair is not a monolithic reputation. It's a bundle of different audience-specific perceptions. It's way more in the minutia of perception. Actors should care about maintaining a favorable image across key stakeholders because their image affects their perceived legitimacy, and it affects the regulations that they have coming around them, and it affects their sales, it affects their support that they have from the public. Communication in this case is considered to be the primary tool in which one can repair image. If the work of Benoit and collaborators apply the strategy and the taxonomy to high-profile public controversies, which they have, political scandals and corporate failures and corporate scandals and public figure misbehaviors, the case studies demonstrate that actors within these situations rarely use a single strategy in isolation. They don't just use corrective action without mortification and bolstering. They say, we take responsibility. These are the things that we're going to do to make it better. And remember that we have a long record of following through on what we say we're going to do. These are recurrent when that party is definitely guilty and responsible. That's difficult to deny. So that pairing can generate some prescriptive guidelines for organizations. When you're responsible, admit fault, apologize, go through with the corrective actions. If you didn't do anything, denial is legitimate though, and that can be paired with bolstering. So that is a tour through a crisis communications seminar. Hope you enjoyed that. Let's lastly talk about AI weather models. Before we do that, I want to show you a conversation about what a scientific description of weather predictions might sound like.
So, the million-dinar question. Are we saying it's going to snow tomorrow? Or it might?
Let's start with what we actually see. ECMWF gives us what? A good, solid band of precip over us by 6 a.m. Temperatures flirting with zero at 900 to 1,000 meters. At 6 a.m., about 65 to 70% of the ensemble members give us accumulating snow above 900 meters. Another 20 to 25% keep us mainly rain, maybe wet flakes on the hills. Small tail, say 10%, gives a colder solution with decent snow even in the mid-elevation neighborhoods.
So central tendency might imply snow on the hills. The spread explains, though. Don't get brash.
Let's separate two things: what the data say, how confident we are. On the data, there will be precipitation. That's high confidence. Temperatures are marginal. That's medium to low confidence for snow at city level. High elevations, I'd say we're in likely snow, but watch the exact line.
If a reporter walks in right now and asks, will there be snow tomorrow in the city? What do you answer?
Yeah, so roughly a 40% chance of accumulating snow and a 60% chance it's mostly cold rain. For neighborhoods above 900 meters, the odds flip. We're more likely than not to see some snow, but the exact amount depends on how quickly the cold air deepens overnight. We're always updating forecasts as new data arrive.
I wanted to briefly talk about the different forecasting groups, specifically an AI model called Pangu. And AI weather models are exciting, they're fast, they still struggle with rare occurrences, rare storms in this case, things that might be considered weird, especially typhoons that suddenly change direction, or a cyclone that suddenly changes direction. So in plain language, my understanding is that this, for decades, the weather can be relied on by accounting for the numerical weather prediction, or NWP. This is the big physics machine. It's crunching millions of equations. It's trying to simulate how the atmosphere is going to move. Those models are the backbone of real world forecasting. AI models over the last couple of years have machine learning in that they are taught the weather model patterns from past data. Instead of solving equations from physics step by step, they don't know the physics. The famous new Pangu weather model is claiming, though, that it can predict weather incredibly fast without losing accuracy. This is a very new technology. It's going to be faster and accurate, is what they claim. The problem, though, is that extreme weather events are occurring more routinely, and we constantly have to adjust the model for what we consider to be normal weather patterns. An extreme event example wasn't actually about path weirdness, though. The original Pangu weather paper showed two typhoon examples to claim that it could identify extreme storms, the Kong Ray and the U2, and it said, look, Pangu predicts extreme storms. But this commentary also pointed out, and that's why it's so important to read the actual commentary, and not just the headlines, because those storms were extreme, but those storms were extreme because they were strong, not because they took a different path during their trajectory. The original claim created the impression that Pangu was good at predicting weird typhoon weather without specifying what that prediction meant, because that wasn't actually what was tested. Pacific found that, let's see, how good Pangu is actually at predicting the strange typhoon paths. The ordinary typhoons, those are easy to learn. It's pretty good at that. They go where one would expect, but those turning typhoons, they're going to take sharp turns. They're going to loop. Some of them will loop, and these are a perfect example of, for the issue with AI models right now. Pangu errors were 7 to 19% worse than the ECM data from the European agency that I think I discussed. The longer the forecast, also the faster Pangu skills dropped. So after about, I think it was after 3 or 4 days, the skills dropped pretty significantly. So as the storm continued to transpire. So this is the extreme behavior of test forecasting systems. Why does AI struggle with some weird stuff? Well, if an event is rare, like a typhoon or cyclone that's suddenly turning, the AI model does not have examples of it yet. It hasn't learned that that's possible. Another issue with this is that they found that AI weather models can produce unrealistic predictions that are not bound by physical laws. Traditional weather models explicitly comply with those rules because they solve physics equations that govern the real atmosphere. But the AI models don't know physics. They only know the patterns in historical data. They don't actually make sense physically sometimes also in their predictions. They sometimes make predictions about things that could not actually exist in the real world. That doesn't make AI models wrong in a broad sense. It doesn't mean that they can forecast misguided predictions that look plausible and sound scientific and confident, but fail at basic physics tests. Let's think about how AI models should address their own uncertainties with the public, how an image strategy from companies or from institutions that are designing and employing these models might use image repair strategies when a model gets it wrong. Europe's gold standard model, the ECM, is a comparison point for Pangu. When it came to a typhoon called a typhoon Cannon, that's Hanun, in 2023, this is another good stress test storm, the kind that meteorologists worry about because it doesn't behave politely. Cannon did 2 sharp turns within 5 days, though. The contrast is clear. The ECM physics-based model integrated high-resolution physics and solved the equations by considering winds, pressure, moisture, energy, and they used an enormous observational output to from their satellites and from radio, like we were talking about at the beginning, the buoy data that we discussed at the beginning. And if the physics says in this case that a storm is about to turn, that the model can't ignore it. But compare that to the Pangu weather AI based model. Nothing against AI, by the way. I don't have a strong position either way. But it's worth discussing that the AI model, Pangu in this case, learns patterns from historical data, but it doesn't know physics. It struggles with events that are rare in its training data set. In other words, if it hasn't been trained to identify storms that take this sharp turn within 5 days, they will struggle with events that are rare in the training data set. When typhoons, cyclones, blizzards are acting weird according to our assumptions, the physics models still succeed. What this tells us about uncertainty and conveying uncertainty to the public is that when the ECM forecast for a storm like Cannon is presented, it doesn't simply spit out a one track single. It gives forecasters an ensemble of dozens of possible tracks. Not necessarily the greatest, not necessarily the greatest hits, every possible scenario, and is accounted for. And they spread those tracks. And that's the uncertainty that the interviewee was discussing in her conversation that I presented. It was just a hypothetical conversation, by the way. Every possible scenario, and they spread those tracks. This is the uncertainty. Forecasters would see a tight cluster of that spread and a tight cluster that they would say with high confidence is going to happen. High confidence doesn't mean certainty, though. If it's a wide cluster, it's low confidence that could happen. And outlier tracks, if there are possible sharp turns, like with Cannon, and alternate landfalls, or 36-day trajectory like Freddy, then we move the spread over time. The confidence is increasing and collapsing. AI provides a single trajectory, though. It is a one-liner. It's one line on the map. So even if internally the AI model knows that it is unsure, it won't show that to the user. This is where it becomes important to consider the way that we convey stakes, the way that we present information as certain or as confident, and basically how AI gives the appearance of certainty when the underlying signal is deeply uncertain. AI forecasts are clean, fast, and visually appealing, but they risk being misunderstood as more certain, even as the physics models are not. Just like the Arabia weather when communication crisis moment in 2019 had a deterministic sounding snow forecast and busted, the AI models faced a similar trust erosion if one stunning failure shakes the public confidence. It shakes public confidence because it causes a real consequence. The stakes here could be governments relying on AI for evacuation decisions, cities using emergency resources based on AI timing, the public forming expectations from AI products from private companies and weather apps rather than their understanding of how science works. So a single AI failure on Cannon or a Cannon type storm could undermine the entire category of forecasting with machine learning. AI models need to show their confidence, but more than that, they need to show their output. The most important thing is to understand that an AI model cannot necessarily express mortification in the way that a Benoit style image repair strategy might be able to when uncertainty is baked into it. How should AI models express uncertainty to the public? What are the minimum transparency standards for those outputs? What does it mean? What does a minimum transparency standard mean? Is it layered in 4 dimensions of meaning that can only be understood in a court of law? And if so, how can we make it easier to understand? How should this ensemble uncertainty be constructed within AI models? And then a couple of other questions is when should the AI hybrid system defer to NWP? Should there be a point when you have AI running in part of your model and does it transfer the information that need to be processed? When does it do that? And then lastly, what are the obligations of agencies using AI forecasts? This goes for agencies that don't use AI forecasts also who are using NWP. So I'm using a lot of acronyms, right? But these models need to evolve beyond pattern engines into trustworthy institutional forecasts. And that means that they show uncertainty and explain limitations, integrating physics, adopting a crisis communication logic, and design for some sense of reasonable humility and confidence as well without the sleek certainty. Otherwise, AI models are going to repeat the same shocks that we see in forecasts to a degree that is less adjustable in the way that the physics models can adjust. People already know that their weather app is sometimes wrong. People already know that their GPS sometimes reroutes them. They already know that their Spotify is occasionally going to whiff. But what bothers people is not that imperfection. It's the surprises. It's the you sounded 100% sure. No one told us that the forecast might change that much, and you're acting like you didn't just say that, or you did say that, and you're ignoring that we had that conversation. Instead of saying snow is coming on Wednesday, then we could say, here's the third. We could say, Here's the Wednesday forecast. We'll update it at 8. We'll update it at 4. We'll update it at 8 p.m. These things, as we come to the end of another episode, let's return to, as we come to the end of another episode, let's return to the reality that was at the core of this forecasting episode, which is that weather models, whether driven by neural networks or physics, are ultimately our best efforts to map a restless, spontaneous, and complex environment that owes us nothing. I wish you good weather and even better predictive models, a horizon, and the hopeful smell, a clear horizon, or the hopeful smell of some incoming rain. Be inquisitive, be ready. May your decisions mostly fall in the realm of possibility. Until next time.